Welcome, everyone. It's my pleasure to introduce our robotics seminar speaker, Professor Zac Manchester. Zac is an assistant professor at Carnegie Mellon University. He got his PhD and bachelor all from Cornell, and later worked as a postdoc in the Agile Robotics Lab at Harvard. He has also worked at places like Stanford, as an Ames Research Center, and Analytical Graphics. Zac has received the NASA Early Career Award, the Google Faculty Research Award, and several Best Paper Awards. His research interests span a lot of topics, ranging from planning control, numerical optimization, to spacecraft flight navigation and control. I want to highlight two projects. One is called CubeSats, a small satellite swarm that can be launched in space. Zac has led 4 satellite missions. The other is an open source solver called TinyMPC. It runs on very small memory footprint and gives very good performance. And the work has received Best Paper in Automation, and it's also the finalist for Best Conference Paper in ICOR 2024. So a lot of very exciting work. With that, the floor is yours. I look forward to your talk, Zac.
Cool. Thanks so much, Kevin. And thank you guys for the invitation. Super fun to be here. I guess as a, for me, I would love it if you guys hassle me with questions and don't just sit there and let me talk at you, because it's way more fun, and I'm very happy to kind of go totally off the rails. So yeah, please speak up and interrupt me. And yeah, first I would like to inundate you with cool-looking videos so you think I do cool things, and then I think I'm going to at least tease like each one of these at some point in the talk. But if you want to know more about any of this stuff, definitely bug me. Okay, here we go. So I am a space nerd, as Kevin kind of alluded to. My background's in aerospace, and this is one of my favorite robots. It's like Mars Perseverance, right? So everyone's seen this thing. This guy has been on Mars for 12 years, and which is amazing, right? It's super impressive as an engineering feat. In that time, it's driven about 32 kilometers, also impressive. But when you divide those two numbers, it's a lot less impressive. This thing is, on average, driving about 7 meters a day, so like across this room or something like this, right? Which is sort of disappointing. And this guy, there is a whole autonomy stack on here. It can drive autonomously, but ultimately, the thing that like really limits, this guy's ability to drive around on Mars and do cool science, I think, is nicely summed up by this picture. Does anyone know what this picture is? Has anyone been here before? So I see some nods. Yeah, so this is the Mars yard at JPL, right? This is this big sandbox out back at JPL where they have like a backhoe and a bunch of shovels and sand and rocks and things like this. And so the rover drives around autonomously as long as the conditions are benign and the ground's relatively flat. There's no big rocks or slopes. But if it runs into any of those things, it basically stops, takes a bunch of imagery, and then phones home and says, I'm stuck. And then the rover drivers at JPL go out back to this big sandbox. They take all the image data, and they basically try to recreate the environment around the rover on the ground in the sandbox. And then they drive around and practice all the possible things that could happen and decide exactly how they're going to drive the rover. And then once they're happy with that, they uplink those commands, and the rover executes it and then keeps going, right? So I guess the other thing to mention, right, is that JPL actually, more or less works on like 9 to 5, Monday through Friday work hours, and they take holidays and stuff like this. So if this happens on like Friday night, it doesn't get fixed till Monday. So there's actually like long periods of time where this thing's just sitting there, being stuck. So I guess to end that conversation, this rover is not very autonomous, right? And it's really limited in that in its locomotion capabilities, and needs a lot of human hand-holding to do all this stuff. And I think ultimately what we'd all like is, I love watching these kind of videos. Like, these guys are incredible. They can navigate through, unstructured, extremely rough terrain, and, kind of plan really dynamic motions in ways that we still are, just nowhere close to with our robots, right? So I think this is the dream. Okay, hopefully I've gotten you all excited now, and I'm going to now try to indoctrinate you with my worldview, which is everything is optimization. So my kind of pitch here is that almost all of the pieces of this autonomy stack, right, that we need to do things like this, at least can be posed as optimization problems, and maybe that's a good idea. So the first one that I think everyone will appreciate and be familiar with is, control can be posed as optimization problems. And I think this is very broadly construed, right? Like, I'm not going to take sides on, if you want to do MPC or RL or whatever. It's all kind of the same thing, right? You write down a cost or reward thing that says what you want to do. You have a model of your robot with your dynamics, which could be F equals ma, or it could be some kind of simulator, or it could be a learned neural network model. Maybe you have some constraints that sort of define the limits of your hardware or safety or whatever. And then, yeah, you have this kind of objective thing that a reward or a cost that sort of encodes behavior, right? Like, what do you want the system to do? And you can write this thing down and then discretize it some way or whatever, put it on your computer, turn the crank, and hopefully get something reasonable out that you can run on your hardware, right? So we've done a bunch of, I'll like highlight a little bit and tease a little bit of the stuff we've done in each of these little areas. So this one, as Kevin mentioned, we did some work recently, I think in two kind of interesting directions that we've been pushing on the last couple of years with regard to what I'll say is scaling of these methods. So we do a lot of MPC. We had this paper called Tiny MPC where we developed an really, really lightweight solver that can run onboard tiny little resource-constrained microcontrollers. So this is running onboard a Crazy Fly. It's a little STM32 like ARM chip at like 200 hertz. Can do real-time obstacle avoidance and fly around on this guy, all on board, which is kind of cool. So this is like one extreme of the scale. And the other extreme we've kind of been really into the last few years is trying to figure out how to really exploit modern computational hardware to do this stuff faster. So it turns out a lot of the solver algorithms we use, particularly for MPC, are still very serial and single-threaded and run on CPUs. And we still really haven't figured out, I think, generally how to exploit GPUs and large-scale multi-core kind of processing hardware to do this stuff. So this is like the first thing we came up with in several years of poking around that actually worked. It's called ReLU QP, and the idea was we figured out a way of basically analytically transforming QPs into ReLU networks. So there's no learning involved. You give me a QP, I can analytically derive the weight matrices and throw it on a GPU. We're able to do things like, this is whole body control on Atlas, so relatively large state and input space, relatively long horizon problem. This is running at 2.5 kilohertz. So like order of magnitude faster than we can do right now with kind of off-the-shelf stuff. So I'm really excited about this stuff too. I think this opens up a lot of interesting ideas. Okay, so cool, that's control. State estimation, perception. These things, I think, also you can pose as optimization problems. Interestingly, this looks almost the same as that control problem, right? There's this duality ideas, model, whatever. Now this is a least squares loss that's trying to match up your state to your data. So we've done a bunch of stuff in this area too, using very similar algorithms, right? So I'll highlight a couple of these. This is kind of more on the space side. So we actually build and fly satellites in my group. This is a mission we flew this year, or like 2024, that actually just ended, called Pi-4, where we flew a little swarm of satellites in low Earth orbit. They talk to each other with cross-link radios, and they can do two-way time of flight ranging between each other. And we're able to do kind of full 3D relative pose, basically, like relative orbit determination, using those signals and some other stuff. And we actually did this in space on orbit and got 70 centimeter level, kind of 1 sigma relative navigation going on these things autonomously. It was really cool. We also built all the hardware in-house. This was really like we did all of it, which is pretty cool that we got it to work. And then another thing that we're getting into now that I'm pretty excited about is vision-based orbit determination. Well, actually, orbit and attitude determination. So I call this the lost in space problem. So if you fling a satellite out in orbit, it has no idea where it is, and it just has onboard cameras. We're trying to figure out how to take images from those cameras and then not only reconstruct instantaneously the pose, but like predict the orbit now and all that good stuff. So there's some machine vision in here and a bunch of cameras, but at the end of the day, it turns into this fun little optimization problem. Cool. So okay, so far we got control, state estimation, and then this one is a little weirder, but like very kind of near and dear to my heart. Who knows what that thing is? This is like Hamilton's principle, least action principle, right? So I think everybody's probably seen this once in like their mechanics course, and then you did some weird calculus of variations stuff and got like the Euler-Lagrange equation, and then you never thought about this again, right? You just get your manipulator equation and you're happy with that. I'm here to tell you that maybe this is worth thinking about a bit more seriously. So to be clear here, right, this Q thing, this is your pose, your configuration. This L thing is Lagrangian, so kinetic minus potential energy. Probably all seen this before. But instead of kind of turning the crank here in continuous time and like variational calculus stuff, instead what we're going to do is directly discretize this integral. And the thing I'd like to point out before we do that is that if I kind of like squint at this a little bit, and I imagine that Q being an X and that Q dot being a U, this is exactly an optimal control problem. In fact, there's an exact mapping between this problem and an optimal control problem. It's called the Hamilton-Pontryagin principle, which is obviously suggestive. So this is like, basically we can play the same set of tricks we use for solving control problems on this. So I can discretize this and basically solve it like a control problem. So you might ask why I would ever want to do that. And the answer is, with the standard kind of stuff we're used to doing to solve these problems, like simulator, whatever, it's really kind of tricky to deal with complicated constraints. If I do it this way, I can easily include things like inequality constraints. And in particular, inequality constraints are super, super useful in this context for modeling non-smooth mechanics. So if you think about impacts in particular, so imagine we have a brick here, and then this phi function over here is a sine distance function, which is telling you the height of the brick above the ground. So if I just write that inequality down that says the brick's not allowed to go through the ground, and solve this in using standard constrained optimization ideas, throw it in a solver, what comes out of this is really cool. Like you'll get physics with inelastic impacts, and the Lagrange multipliers of that constraint end up being the impact forces, like all these kind of really cool things you expect. And unlike a lot of classical methods, you don't get stiff ODEs. It all just kind of works. So this is kind of cool. As another teaser for some other stuff we've been working on the last couple of years in the lab, it turns out this exact approach where you kind of look at this in this kind of constrained optimization perspective, we've also applied this to fluid mechanics. And we've been working on like fluid structure stuff for swimming robots, and we've finally started to get this stuff to work. So the thing on the right is like trying to do the famous like dead trout experiment where you swim upstream passively. And then the thing on the left is a robot we've been building recently that's swimming in a little kiddie pool, and the right is the simulator, and the left is the real hardware. So kind of cool. Like, and the idea here is the inequality. The constraints here have to do with how you match up the robot with the fluid. So you're basically classic, like if you've ever done this before, the no-slip boundary condition, or sort of the idea that the fluid's not allowed to penetrate into the robot. That's really naturally posed as a constraint. And the multipliers there end up being the pressure forces. It's all like really, really natural. And the last thing I'll mention in this kind of vein, because it's going to come up later, is that friction, which is also non-smooth and annoying to simulate classically, can also really nicely be posed as an optimization problem. So this is called the maximum dissipation principle. Basically says that friction, which is the B in here, the friction force due to Coulomb friction is the one that instantaneously sucks out the most energy from the system, subject to this constraint here that's called a friction cone. So this is saying that the friction force has to be less than or equal to some friction coefficient mu times the normal force lambda. And the idea here is that if I imagine like a brick sitting on a table and I'm pushing it, it'll stay put for a while. And that corresponds to this B, this friction vector being inside the friction cone. And I keep pushing a little bit harder. Eventually it's going to get to the friction force will get to the boundary of the cone. And if I push a tiny bit harder, there's no more friction left. And that's when it starts moving, right? So that's captured, that non-smooth stick-slip behavior falls out of solving this constrained optimization problem. It's kind of cool. And then the last one, in this general whole like mess of everything's optimization that I'll mention is we've done a bunch of work also recently. One of my PhD students, Kevin Tracy, basically showed up with this idea, and I loved it, and it's beautiful. It's posing kind of collision geometry problems as a constrained optimization problem. Yeah.
Right. So you solve like friction as optimization
Mm-hmm.
problem, and if you find, I guess, friction, right? Like, what would you? The only application that I can think of is just like use it in a simulation.
Yeah.
You kind of build it in a simulation like that. So like that's like kind of different from what I had normally experience. So like, is that a good application? Or
Yeah, I mean, that's what we're doing with it. I think that's reasonable. And I'll explain a little bit more like why that's maybe a good way to look at it. Okay, so yeah, so you can do collision checking. There's lots of cool things about this too. But I think in the interest of time, I'll probably skip ahead. But if you want to talk more about this, I'm very happy to. There's a paper called Decall if you want to check it out. Okay, so now the question is, how do I put all the pieces together, right? So I've said, we can pose all these things individually as nice, clean little optimization problems. But ultimately, if I care about doing, control, motion planning, whatever, I need to put all the pieces together and somehow couple all these optimization problems and solve them jointly to get this top level answer that I really care about. And this is kind of tricky, and this is kind of what we're going to build up to and try to do. So the first thing I want to do is just kind of have a little interlude for the uninitiated in the room who haven't looked at kind of contact stuff and like robotics, like locomotion, manipulation stuff. So this is all nice, and we can do nice like trajectory optimization or RL in this thing. But a lot of the algorithms we use, this is less true in RL that's doing like derivative-free stuff. But if you use gradients, there's kind of this restriction that your dynamics and everything in the problem has to have reasonable gradients for me to go solve this problem with gradient-based optimization. And in this kind of context, when I have a foot slam into the ground, the dynamics are non-smooth, and this causes all kinds of problems and makes gradient stuff bad, right? So that's kind of what we're trying to get around. One way around it, which is kind of the classical approach, is what people call hybrid methods. The idea here is if you have some oracle or some heuristic or whatever that can tell you when the feet are going to make and break contact with the environment, you can essentially pre-specify that in your motion planning problem and get rid of the hard impact sort of stuff from the dynamics and only optimize over the smooth segments between them. And this, now you're back to a problem you know how to solve and life is good. This can work super, super well, right? So to be clear, right, this is like basically, you know, what this kind of stuff is doing. And this is incredible. I don't want to downplay this at all, right? Super, super amazing. But I now want to point out, like, we'll go watch the blooper video, which these guys very, very nicely put out, you know, for us. So there's something I want to like emphasize and have you pay really close attention to in a second. So this. So watch this guy. Why did that fail? So well, I think probably there was a little hand slip, but I would argue like the thing that really sticks out there is that there was a contact with the toe while it was hopping over that block that was unplanned, right? And so if you're doing this hybrid stuff, you're kind of like pre-specifying which parts of the robot are in contact with the world using some heuristic or whatever. And the controller that you're running, that model predictive controller, it can't reason about the contact. So essentially, one way of thinking about this is the model predictive control algorithm on here is running open loop on the contacts. So in that kind of situation, if there's an unplanned contact with a different part of the body, if your contact mode planner thing didn't tell the MPC controller about that, it just doesn't know. So it has no idea that there's forces that can be, you know, kind of applied there. It doesn't know what to do about it. It just deeply, you know, can't reason about this in a real way. And this is kind of a deep issue. So the dream here is what people have called contact implicit. So this is like, I basically want to be able to optimize over not just states and controls, but also contact forces. And you know, just do all the things, have all the physics in there and get it all out at once. The problem is historically, this has been really hard numerically to do. There's all kinds of, you know, stiffness issues, numerical issues, right? Okay, so now we're going to kind of try to zoom in here and explain how we're approaching this. And this is kind of this idea that I've kind of called composable optimization. So the idea is all these blocks are optimization problems. I'm going to zoom in on one of the blocks and kind of explain, you know, how we solve it and like one standard algorithm for solving one of these things, and then zoom out and show how we connect them. So let's take one of these, right, for instance, and let's say, for example, this is that friction problem. And to harp on a little bit, right, there's an x and a y here. I'm minimizing with respect to x. So that's what we'll call the decision variable. And then y is some other vector, some other set of variables that we're not optimizing over, but the solution depends on it. So we'll call this like a parameter vector. Okay, so if this is the friction problem, we've got our friction cone. This x will be the friction vector that we're solving for. And for example, this y would be the normal force. So that shows up in that cone constraint, but we're not optimizing over it. And in particular, that normal force is coming from one of the other blocks. It's coming from the sort of impact dynamics, least action principle sort of block, right? Okay, so if I take this thing, and the first thing we're going to do is try to get rid of the inequality constraint. We're going to play this trick called a log barrier. So we're going to take that inequality, bury it inside a log, and put it in the objective function. This is kind of very, very standard interior point method stuff if you've seen it. If you haven't, this is basically what it looks like. So I take that, I put this what's called a barrier function in there, which is kind of a smooth function that blows up at the constraint boundary. And the idea, the reason they're called interior point methods is if I start in the interior here of the feasible region, I will never, you know, as long as I sort of do the right things in the solver, I'll never go outside of it. I'll stay in the feasible region because the cost blows up to infinity at that boundary. So it'll kind of keep me on the rails, right? And there's this kind of fudge factor. We call it the barrier parameter or central path parameter, this rho. And I can kind of crank that rho from a very relaxed value that makes this thing nice and smooth and gives me very nice gradients down to a very, very kind of almost brick wall, very, very tight solution. And there's nice ways of doing this. There's all kinds of, you know, theory about this. It's textbook stuff in optimization about how to crank the rho properly and how to make these things converge. But the main point is, you know, I didn't invent this. This is like in textbooks, and we know how to do this really well. Okay, so if we do this, I've kind of gotten this down to like this nice little minimization problem. And the key trick in here we're going to try to develop what I call a differentiable interior point solver. So if I take this thing and I write down its optimality conditions, this is like set the gradient equal to 0, basically, of that optimization problem. That's this like r, x, y thing equals 0. So we call these KKT conditions, but really you just have to think about set the gradient equal to 0. OK, so if I have that guy, I can then play this trick called the implicit function theorem. Who's seen this before? Like a decent number of people? Yeah, everybody, great. So the idea here is if I just diff that thing with respect to x and y, I can kind of rearrange things and solve for dx dy, the derivative of x with respect to my parameters y. And now if I do both of these things, I can think about this entire block, this entire optimization solver thing, as just a function, just any other differentiable function, x of y. And so I can query this. It doesn't matter that under the hood there's some solver. At the end of the day, if I zoom out and I just think about this block, it's some function x of y, and I can get both the function value and dx dy. And I can just think about it as just another function. So now that this is just another function, I can kind of think about burying this in costs functions or constraints or other places inside these other problems and kind of gluing these things together, right? So that's kind of the high-level trick to make all this work. OK, so now I want to talk about some stuff we're doing with this or have done with this. So first thing is if you put like these blocks together, if you do impacts, friction, and collision stuff, you can make a simulator. So we kind of did this. We called this Dojo. And this does some cool things. So one is that it can do real hard contact simulation. So if you've played with robot simulators in the past, you might be familiar with, they do generally a lot of like smoothing tricks and approximations. You often get artifacts like interpenetration where the feet sink into the floor. You get creep where it's not exactly doing stick slip. So we don't have any of that because we're basically solving these constrained optimization problems to convergence. And the constraints are explicitly in there. So if you solve that thing to convergence, you get a feasible solution. It's not going to do any of those things. There's also really nice, I didn't talk about this earlier, but this kind of optimization-based way of simulating the dynamics by minimizing that action integral. This is called a variational integrator. And this was Jerry Marsden at Caltech and a bunch of his students worked on this stuff kind of in the early 2000s. And there's a bunch of really cool properties that these things have. In particular, if the system's conservative, these things more or less exactly conserve energy and momentum. They're super stable. You can take big time steps with them. They do a lot of cool things. And then finally, we can give you smooth gradients to do downstream optimization out of this thing. And this sounds like having your cake and eating it too. Like I told you, we can do hard contacts, which are not smooth, but I can give you smooth gradients. So kind of what's going on there, that feels weird and wrong. So the idea is, when I solve these problems, I have that little row in there, that barrier parameter, and I start out with it super smooth and relaxed. And that gives me nice gradients, and that's why interior point methods work. It's because in the beginning, I smooth it out, and I can take nice optimization steps and have nice smooth gradients, and then I gradually crank it down until I converge. So if I kind of visualize that here, it looks like this, where the pink lines are different values of rho. And if I am doing this inside my solver, I can cache all the previous iterations for more relaxed values of rho on the way to the black curve, which is the fully dialed kind of converged solution. So the black curve is the correct solution. I can solve for that. But then if I want to, I can take one of the cached gradients, so any of those pink lines. So I give you the real hard answer, but I can give you a smooth gradient. And it turns out combining those things can work really, really well in practice. So I'll show you some of that. There's one other thing I want to point out too, though, that's a little subtle and I think underappreciated before I do that, which is this. So I call this weak versus strong coupling, which is a thing that I stole from the CFD community when I started doing that weird fish stuff. I learned about this. So that's what they call this. But I haven't seen a lot of people talk about this in the context of like multi-body simulation. So the left side of this is what I call weakly coupled. And this is actually what I think most robotic simulators are doing. And the way to think about this is if I have these two blocks, and they're kind of going to fall on top of each other, and they're exactly face to face, what's the closest point between those two blocks? It's any point on the face, right? It's like a degenerate case. It doesn't have a unique solution. So if I just have some collision library, and I'm querying that and asking it for the closest point, and then taking that and plugging it into my dynamic simulator, if I query it for the closest point between these two blocks, it's probably, there's no unique solution. So that collision checking library is going to do something reasonable and like regularize that solution and probably give me like the centroid of the faces, something like that, right? And that seems perfectly reasonable if you're just thinking about collision checking. But once you pass that over the dynamic solver, and this thing is having to reason about masses and inertias and accelerations, you get stuff like the thing on the left. And essentially what this is saying is like, if I don't reason about the physics when I compute this closest point thing, I can't really actually balance these blocks on top of each other when they're off center. It just doesn't work, and you get weird behaviors like this. So that's where that's coming from. So what's happening on the right, which is what I'll call strongly coupled, is what we're doing inside Dojo, which is we're hooking these two blocks together, and we're jointly solving them, such that if I look at that impact calculation where I ask for the closest point, if I solve it together with the physics problem, remember that physics problem is solving this least action thing, where it's like minimizing energy. And if I solve those together, it turns out that minimizing energy objective from the physics problem actually regularizes the closest point calculation and makes this thing return the point that minimizes the action, which turns out to be the one where they balance. And because the other one's artificially injecting energy into the problem. So there's some deep connection here where like doing this together actually gives you the physically correct answer, where doing them separately and like not reasoning about how to properly connect them does not, right? So to be clear about exactly what we're doing, so this is kind of the setup. So we have these two blocks, and I set the gradient equal to 0 for each one. So like the top one, I'm setting the gradient with respect to x equal to 0, and I get this r of xy. The bottom one, say I'm optimizing over y, so think like friction and then the impact physics, right, that we just talked about. So the other one, I'm setting the gradient with respect to y equal to 0, and I get this other set of optimality conditions s, right? So I have these two sets of conditions. I stack them on top of each other, and I jointly solve them with, in our case, Newton's method, but you could do other things. But the idea is I'm jointly solving this coupled set of conditions simultaneously, right, to get everything to sort of satisfy. And that's what's giving you this really nice kind of strongly coupled thing that's doing the right thing. And so some of the stuff we can do with this, right, is, for example, like you can do trajectory optimization, so you can just throw this, into standard algorithms, and like that's what that hopper is doing. You can do RL, so the half-cheated example here is doing like just vanilla gradient descent, so no like stochastic gradient stuff. It's actually just evaluating the gradients through the simulator and doing a line search, like the most basic thing you might think about doing. The top right one is doing system ID, so we're doing rollouts, and then we're calculating gradients and trying to fit the geometry and mass properties of that box just from, say, pose data. And the bottom one is doing some sample-based motion planning where we're using the gradients. This is Tao Peng's work that we kind of implemented on top of Dojo to do some like manipulation planning stuff. So a whole bunch of things. This is to say, right, like these smoothed gradients combined with the hard physics answer, they give you useful gradient information for doing downstream motion planning, state estimation, RL, whatever you want to do. Okay, so that's sort of the physics story. So now I want to talk about like the whole thing. So we care about doing motion planning, trajectory optimization, all the above. So we want to put all the blocks together. So we did this, and you can get cool things to come out. Like there's a couple examples, but the sad thing is that these examples take like order 10 minutes to optimize just those like few seconds. This is very slow. It's not, and I want to do this online in real time on the robot. So then we started thinking about how we could approximate all this stuff to make it fast. And so I'll talk about that a bit now. So first one is, so I solved, let's say I solved the planning problem offline. I solved this whole thing from scratch, and I got a solution. Okay, so now given that solution, I want to go run it on the hardware and sort of stabilize it, track it, mop up errors, that kind of thing. So I'm going to first, inside that control problem, I'm going to replace my general objective with a tracking cost. So I take the reference solution that I solved offline. I'm going to put a quadratic tracking cost on that guy that just says stay close to the reference. So that makes that easier. Inside the dynamics, I'm going to go and linearize the robot dynamics about that reference trajectory. When I say linearize, what I mean is I'm not linearizing anything to do with the contact. I'm keeping this entire setup. These are all still constrained optimization problems. But inside that, where the dynamics, the floating base dynamics of the robot show up in there, instead of them being nonlinear floating base dynamics, I'm locally linearizing them and getting sort of an AX plus BU kind of thing locally around the reference. Similarly, in here, where I'm doing this collision checking stuff, rather than solve that problem from scratch, I'm linearizing it around the reference again. So I'm like linearizing the sign distance function to make this thing faster, cheaper, easier to evaluate. And then we're also going to linearize the friction cone. So this is a common trick. Rather than use a round like ice cream cone, we're going to turn it into a pyramid. which makes them linear constraints instead of sort of nonlinear constraints, basically. So all of this makes the problem a little easier, essentially. So now having done this, this was like the first kind of experiment that really convinced me that this was sort of worth doing. So this is in simulation. This is a quadruped. This is what we call a point foot model. So it's a single rigid body with point mass feet, which incidentally has the same state dimension as the full quadruped, but it's a little bit easier to deal with. Essentially, all we're doing is abstracting away the leg kinematics, which is sort of standard anyway in a lot of controllers. So what's going on here is I have a nominal trotting gait that this thing is executing at the origin. So it's standing in place at the origin, trotting. That's it. That's all I give it. I linearize about that, and that's the thing I'm tracking. So given that, what's happening in this sim is I'm running the tracking controller. I kick it really hard, so it's flying through the air. And you'll notice, right, it's flying through the air. It's kind of flailing around a whole bunch. And then it hits the ground. Yeah, I feel like there's a bunch of really cool things happening, right? So in the air, it's doing this kind of funny move with its feet that's sort of like flailing your arms, right, to try to have it not turn over. So all of this is just emergent right out of the. So okay, it flails around, keeps itself from falling over. Then it's putting its foot out to sort of catch its fall and sort of arrest its momentum. And then it trots back to the origin super smoothly. So all of this is coming out of this one linear model that we linearized about the reference trot, right? Like nothing extra. And this we can solve online at like 100 hertz. So this is like real time. So yeah, I don't know. I think this is kind of a nice story about the power of linear models. We put this on hardware, so you can do it. It runs fast enough. And what we're kind of trying to do now, which this is kind of a little bit dated now, but we've got some newer work on this that I'm pretty excited about, which is, I think, basically the story here is because we have all of the body geometry in here, and not just like point feet, we can do other things. We can do contact-rich things with the environment. So we can do weirder stuff. And right now, we're kind of working on stuff a little bit beyond this, where we're trying to do kind of funky climbing behaviors and leverage contacts with the rest of the body, which I think is super interesting. And the solver can reason about that, right? It's got the sign distance function in there. It can kind of think about these things in a deeper way. OK, so that's the sort of control story about this. And now I want to like briefly highlight some of the other things you can do with this setup, this sort of composable optimization idea. So it turns out this goes really deep, and there's a lot of other cool things you can do with this idea of sort of jointly solving multiple optimization problems. So one of the thing on the left is a project we did a few years ago. It turns out this is also encompasses games, dynamic games. So the thing on the left, which I guess I have to replay now because it didn't loop, this is doing autonomous driving and modeling the other drivers as agents in a Nash game. And so it turns out Nash games are a special case of this composable optimization story. I can, each block is a player in the game, and they all have their little optimization problems, and they're coupled, right? So and it turns out we are able to do this efficiently with the same solver tricks. We're able to solve this multi-agent kind of game theoretic MPC problem for, I think, up to about 6 cars at 40 hertz. So it's real time, and you can reason about complicated interactions like merging, how your behavior is going to influence the other drivers, this kind of thing. The other thing, which is the thing on the right, is classical robust control, which can be formulated as like a minimax optimization problem or a Stackelberg game, also falls under this framework. So I can model like games against nature where I have a disturbance that's trying to make my cost bad, and I'm trying to minimize my cost. This kind of setup, you can also model this as in the same setup, right? So kind of cool. There's a bunch of interesting game theory connections. Some other stuff we're messing around with. Dabbling in manipulation a little bit, and I think there's a ton of cool things there. In particular, what this is doing is we're efforts at parallelizing a bunch of this stuff on GPUs again. So we're trying to compute collision geometry, sort of contact geometry here with a really weird, unusual shaped object. So the idea here is, well, just take a point cloud of the object, and all of these contact geometry calculations, the collision geometry calculations we're doing in that optimization setup, they parallelize trivially across points. So if I model the robot gripper as a set of rigid bodies, and then I just cover the object in points, like a point cloud, I can throw this on a GPU, and I can evaluate 5,000 points worth of collisions for the same price as 1 point worth of collisions. So I can do this kind of stuff really, really cleanly. And then some other just random thoughts about this is I think like, if I have a differentiable simulator, so people, I think, are talking about these differentiable simulator ideas mostly in the context of training RL policies. But I think if I had a differentiable simulator, right, and I was thinking about what to do with it, I think an even maybe more powerful thing I could do with this, which I haven't seen a ton of in recent robotics, is like basically system ID or real to sim, right? If I go, say, train an RL policy, run it on a robot, and then there's some differences between what I see on the robot hardware and what I predicted in my simulator, why don't I take that data and then basically backprop it through the simulator to regress all the stuff that's hard to model? And not only can I do like parameter fitting of like, I don't know, friction coefficients and masses, but I could also throw function approximators in there in all kinds of weird places and estimate out weirder kinds of friction models, kind of whatever you want, right? So I think this is also really interesting and powerful and like a thing we should probably be doing with differentiable simulators. Residual learning, take your pick, right? And then lastly, I'll just briefly tease, like one of the other interesting directions we've gotten into recently is doing control for qubit systems for quantum computing. This has been super fun and interesting, but the deep questions here, from my perspective, the dynamics of these systems is pretty benign. Like they're smooth, they're bilinear, but it's pretty benign. They're like benign, smooth, nonlinear systems, and we can do trajectory optimization and all that good stuff to design qubit gates, it turns out. The hard part is measuring anything. So you're familiar with like quantum measurement issues are really weird and it's hard to do measurements and measurements are expensive. So if you just use the nominal model, you might get to like 98, 99%. And to make real quantum fidelity, right, like hitting your target, this is what people care about. And this is not good enough to build a computer because that's on each qubit. So you imagine each qubit has like a 1% error probability. If you have a few of those, it's going to get really bad really quickly and you can't do useful computing. So people want to get to like 5 nines fidelity, like 99.999%. And so to do that, I would argue you really need data-driven control. Like you have to actually calibrate this stuff and do something that's kind of mopping up the error between the model and the hardware. So that's what we're trying to do here. And it's basically, again, this idea of, we're trying to be super data efficient, get the most out of each measurement because the measurements are expensive and they're very noisy, and then roll that back into our model and do kind of more sophisticated sort of data-driven control. Okay, on that note, these are the people who actually do all this cool stuff. Obviously I don't. A bunch of my grad students, some former at this point, recent grads, but they're the ones doing all the real stuff, not me. And with that, I'd love to chat, take questions, and this is how you can, get a hold of me and bug me. Incidentally, that picture is me on the roof with a satellite ground station trying to talk to one of my satellites. All right, cool. Thanks, guys.
So I feel like we have a lot of time. So is there any questions from the audience?
Yeah, when you have stacked 4 blocks, you have these points moving around.
Yeah.
So what happens?
So those are the closest points coming out of the collision checking, if that makes sense. So ultimately, you're querying this thing for what are the closest points between the blocks. And it's ill-posed, like it doesn't have a unique solution when they're face-to-face, right? And that solution jumps around super quickly if you do this, right? So, it didn't actually change. So the idea here is, if you naively do this and you don't couple the physics in, you get bad things. And then the physics sort of regularizes that closest point and it gives you the one that actually, minimizes the action, which ends up being kind of this minimum energy solution where they balance, which is super cool, I don't know, in my opinion.
Yeah, so just building up on top of this, Zach, I'm wondering if you took the Stanford bunny example you were showing and you had like a pile of Stanford bunnies.
Yeah.
And how would that simulation?
I mean, obviously this is going to get nasty in some ways, but I think the message is that it parallelizes quite well across points in this thing. I can parallelize every single collision evaluation individually across the points. So if you want to do a ton of them, maybe doing the point cloud thing is not the best. The reason I think the point cloud thing is interesting, though, is that's natively kind of what we get out of perception systems. So if I was actually trying to do this on a real robot in an environment that I hadn't pre-mapped or whatever, I mean, this seems like a pretty interesting way to do this to me. Like I can grab a point cloud, do some light processing on it, and directly suck that object into my simulator and reason over its geometry and figure out how to grasp it and that kind of thing. If I cared about doing like 1,000 bunnies offline sim, I think probably points is not the best, and you'll start to see weird artifacts if it's bunny on bunny, right? It's not going to go super well. This works because it's point cloud on rigid body, right? If I had to do multiple bunnies, probably what I do, practically speaking, is I would decompose this into a set of convex primitives. So I'd decompose it into a bunch of blobs, right? And then I can parallelize the blob evaluations in the same way, though. So I think the scaling's still like pretty decent. If you can throw this on a GPU, you can do thousands of them in parallel, and it works pretty well.
Thank you.
In the collision setting, yeah, so you can get into trouble for sure. I think like there are definitely corner cases, right? I have to say, and this is, I think in the literature, this has been explored quite a bit, right? Like there's these, like the Penleve paradox and these sorts of things. And I think implicitly we're smoothing these things a little bit with the log barrier. And I think that actually mops up a bunch of these issues where in the limit as that central path parameter gets cranked all the way, the paradoxes sort of arise. But when you back off a tiny bit and you have this tiny bit of smoothing, it tends to, I think, clean this up a bunch. So I'm not like, we haven't looked at this super, super carefully. Like there's definitely weird things that happen in the limit. But I think we've, frankly, we haven't cared too much about that, and it works in practice.
But you don't think non-uniqueness may actually be physical?
Yeah, I mean, it is certainly in certain circumstances, but a lot of these non-uniqueness issues that come up are due to the rigid body assumption, which is not really true at the lowest level. And so with the tiniest bit of compliance, they end up kind of going away. So some of them, right, like the Penleve paradox, like a famous chalk thing, like you can reproduce it in real life and it is a real thing. We haven't actually tried to do that here, and it'd be fun to try. I actually don't know what would happen. Like I haven't looked at this carefully. So yeah, those, I mean, some of them are real, right? But a lot of them, there's like these limiting kind of arguments where in the limit of a true rigid body, you get very weird things that happen. And so, I mean, there's these arguments about, oh, the world's not really rigid bodies, and maybe this is a bad sort of modeling paradigm and whatever. But I guess I'm a very practical person, and I care about like what's happening on the hardware and stuff like this. And yeah, I feel like we haven't really dug into these issues. I think they're interesting. They're like definitely mathematically interesting. So I can't say with any real, determination like what would happen if we checked out these things. But my gut is that the small amount of smoothing kind of makes a lot of it go away. I mean, for sure. I can't pretend to be, have any real insight into that stuff. But I think like at a high level, I think a lot of the things that, animals and humans are doing are like kind of minimum energy flavored. So I think there's a lot to be learned from doing that, which is very natural. The caveat is that like when we do this stuff on robot models, like motors look a lot different energetically than muscles. So like there's been a lot of work on like modeling muscle kind of stuff, and that gets you qualitatively different answers in terms of gates, low energy gates and stuff. So there's a bunch of weird things like this. The thing that I think is, so that's part of it. The other thing that comes up, I think, really quickly when you start doing this and you start doing like minimum energy gates, which seems physically plausible, is that you get really, really brittle solutions. So for example, if you imagine doing like super low energy walking on flat ground, it turns out the energy optimal thing is for your leg to swing like a pendulum, basically, and basically get arbitrarily close to the floor during that swing phase. So like that's the energy optimal thing. And obviously, if there's any uncertainty, you're going to scrape the floor. And this is maybe bad. So there's also this notion of like robustness to uncertainties, that if you just do nominal model and minimize energy, you don't get any of that. And I think that's also a piece of the puzzle in what biology is doing. So I think there's energy, and then there's like kind of actuator mismatch, and then there's also this kind of notion of robustness that we're missing in the naive picture here. But in theory, you could get at that, right, by throwing more compute at it and like sampling over some of the uncertainties and stuff.
Thank you very much for the talk. I wonder if you have like a temporal logic tasks that usually are cast as a mixed integer linear constraints in the optimal control problem. So how this framework is amenable to incorporate such tasks?
Yeah, there's like, I guess, a lot to say about that. So I guess first off, like I think there's obviously mixed integer ways of formulating a lot of these problems, and like I think there's sort of a continuum of ideas, right, around like, you can model like contact modes, right, via mixed integer stuff. And I think there's like obviously good things about that. And then there's, I think the bad thing about that is that in general, you can't really like bound runtimes on those things. Or the worst case runtime is really bad if you have to enumerate lots of these integer variables and do branch and bound or whatever. Like it might be okay, but it could go off the rails and take way too long. And if I want to do real time stuff. So doing mixed integer stuff in real time slightly terrifies me. It has. I mean, I think Russ maybe have some more insight into this and have some other stuff that's like better now. But I think like that was kind of always my thinking, is that I don't want this kind of, even if the average case is sort of okay, like it scares me that I might not get a solution in my, say 10 milliseconds of my control loop, and then I might, break or something. So what we're doing here is like, you could get at for sure by solving mixed integer problems. There's also interesting work that we've also dabbled in where there's natural mixed integer formulations or sort of like switching kind of constraints that you can capture this way. So another way of talking about the stuff that I showed you that I explicitly didn't mention is complementarity constraints. And a lot of people say this, and I think there's something there, but like you can model switching behavior as complementarity constraints, and those can be captured this way. So there's also kind of, it goes both ways. You can do both things. And what we're doing is like very much local. And it's able to reason about some of these switching things, but it's inherently local. So you're not going to get global optima. No hope in general, right? But we can make them go fast, and we can kind of get reasonable things online. If you care about global optimality, then you definitely want to kind of zoom out and think about these, mixed integer things and branch and bound ideas and stuff like this. I don't know. That was a long rambling answer. I don't know if I got at what you were after at all, but we've done some of this. I think these methods are not, they're inherently local. You need decent guesses, but they can be fast. Those methods are going to get you maybe, hopefully, more global optima kind of stuff, but they can take a long time. Sorry? Rigid body assumption. Yeah, okay. Yeah. Yeah. Yes. So we've done cloth, and we've done fluids. So it all fits in the same framework. It literally just is how much compute you can throw at it. So you can do cloth with finite element methods. You can discretize it, right? Like if you discretize the cloth, you can turn the crank and do exactly this, and it all kind of works out. Yeah, I think that's basically the story. And we've done fluid dynamics. We have done cloth stuff. We had some work trying to do like model-based sort of state estimation for cloth manipulation. So we literally made with a collaborator, we got a finite element simulation that could run faster than real time for cloth, and then took like a shirt and put QR codes all over it or whatever, April tag kind of printed on the cloth, and then you drag it around, have cameras on it, and like you use the cloth sim as the dynamics model and a Kalman filter, and you can track the cloth and all the deformation and everything. So it's totally doable. Caveat, right? It gets expensive. Yeah. Yeah.
Solutions, and you're fine and get your task, right?
Mm-hmm.
Can you comment on how high the solution accuracy you need to get accurate?
We absolutely do this, and we don't care, right? So I never pretend, like I don't care about global optimality. Like I don't care about having super accurate, super optimal solutions. I really don't even care about local optimality, to be honest. What I really care about is feasibility. Like as long as it obeys the constraints, obeys the physics, doesn't face plant, I'm happy, right?
Is the sensitivity still accurate?
I see, yeah. So, no, right? Because technically to do that thing, right, it assumes the right-hand side is 0. And so if you haven't converged, it's not, right? So there are some tricks there. Like basically what you can do is if there's a non-zero right-hand side, you can effectively like solve a least squares version of that like implicit function theorem thing and have like an affine kind of equation there. So you can still play some games. Practically speaking, we don't bother with that either. We solve this to coarse tolerances like 1e minus 2 or 3 kind of, and then we just let it run and it works out fine. So yeah, I don't know. We do it in the online context. It's super coarse, and I think the meta insight there that it took me a while to really wrap my head around, like when I started doing all this stuff, is that like in almost every case I can think of, you're always better off running the control loop faster. So taking like one more iteration on the solver to get a slightly more accurate solution, like the way I would sort of talk about it is that, okay, like let's say I have a coarse solution. I could take one more iteration and get a little bit better. But if I've already taken a couple iterations, what I have now is already better than what's on the actuators. So why would I not put that on the actuators now? And then I can take my next step, right, and sort of keep going. But like, you're basically, if you take one iteration on one of these things, you're doing a little better than you were. So you should put that on the actuators right away, right? Like, so just running it faster and kind of doing these, what people call online iterations or whatever you want to call it, right? But basically, like, kind of just updating the commands like as the solver is running, it tends to work out a lot better. And this is generally what people do in practice. Yeah, it feels sketchy. And there's, like, I think, deep questions about convergence and stability of these things that there are some answers to. But basically what happens is if you think about your solver as a dynamical system, you now have a coupled dynamical system where the solver's sort of convergence behavior is tied up with the actual dynamics of the system. And they're kind of all in it together in some weird sense, right? So I think that it's super interesting. And like, I think analyzing that is hard, but it's yeah.
So you emphasized interior point for solving your optimization problems. Why? Why not a first order method, a subgradient method, anything else?
Yeah.
And is it important to that you do the primal and the dual, or are you doing primal only?
There's a lot of answers in there. Okay, so one thing to say is that we actually care about the duals in a bunch of these problems because they're contact forces, I don't know, like all kinds of stuff. So we do care about the duals. They're forces, they're physical things and they end up in the cross coupling. So we deeply care about the duals for most of these, for a bunch of these things. So that's, I guess, item number one. So in general, you want primal dual solutions. Why interior point? It really comes down to this. So we've tried, I should mention that we've tried basically everything you could think of in this space of how to solve these things. And we've done other things that do work out sometimes too. And to be clear, right, we do lots of other not interior point things in other contexts, like the tiny MPC, Rayleigh QPs, those are not interior point methods, those are ADMM. Like, we do all different things, but in this context, it turns out when you're trying to do this like coupling thing and jointly solve all of these problems, the sort of smoothing of the constraints that you get from this makes the gradients well behaved. And often these are really nasty problems. Like, they have all kinds of, I don't know, there's lots of flavors of badness in here. And being able to apply a second order method to it, like just throwing Newton's method at this, works so much better than first order stuff. Like, because in this context, I've got a bunch of problems. The scaling can be all different between these things. So, if you're familiar with trying to do first order optimization, right, you need preconditioning, you need things to be well scaled, you need acceleration techniques, right? And basically, if I throw Newton's method at the whole thing, I don't have to worry about any of that. So you probably could do some first order stuff here, right? Like, and you could probably get that to work, but I think it would be nightmarishly hard to like get the engineering side of that worked out. So practically speaking, I think second order methods are just way easier to tune and make work, and particularly when the problem has some nasty stuff going on.
The drawback of that is that you can't warm start most of these, or have you guys worked specifically?
We do lots of warm starting. Yeah, so there's all kinds of tricks. I mean, this is a longer conversation and pretty in the weeds. I don't know if we want to nerd out about it in front of everybody, but happy to talk offline about it.
So I don't know. I don't want to be that guy because I feel like this is a kind of an obvious question. But so when you did try train, or I mean, I'm imagining you tried training like, an RL agent with like a neural network, and you propagated the gradient like all the way through the physics and everything, and maybe even used like a second order method to solve it. Then, like, what happened?
Okay, there's a lot I guess I'm not totally tracking what the question was in there.
Yeah, I guess my question is, like, you mentioned a couple times that you could use the second order method to like make your RL just like
Okay.
network really fast.
Okay, what are you talking about, training or online?
Training.
Okay, training. Yeah. So the biggest I've dabbled in this and tried stuff. Rayleigh activations don't have second order derivatives.
Right.
So that just doesn't work. So if you use a smooth activation that like has well behaved second derivatives, you can apply second order methods. So like in particular, I think people have tried this, right? You can use LBFGS and stuff like this on big neural networks, and as long as the activations are smooth, this can work, and whatever. So I don't know. I think the real answer there though is that if you're training on GPUs, second order methods don't work well on GPUs. There's like architectural reasons and like software engineering reasons that second order methods are really difficult to implement well on GPUs. Doing sparse matrix factorizations on a GPU is terrible. And in fact, just worse. We've tried all this stuff. Like if you need to sort of solve a sparse linear system, even a big one, it's almost always faster on a CPU, even on a single core, than trying to do it on a GPU. There's just kind of, yeah, doing matrix vector products on GPU, good. Doing like AX equals B, terrible.
Cool. Well, and then I guess for a second question, since I guess I have the last question. So when you ran the linear model, I guess I'm curious about a little bit more details about that. So so the 10 minutes would happen beforehand, and then you would like linearize something, or would you like linearize it online? And I'm kind of curious about what the
yeah, I mean, in principle, you can do all of the above, right? I think there's like a whole space of options there. If you want to think like about something as a planner and something as a controller, like the difference there, at least in this concept, is really just how fast you can run it. So you could think about the like solve it from scratch thing in minutes thing as a planner, and then the linearized version as the low-level controller. And so yeah, you in principle you could, it's all about like time scale separation and like how fast can you solve it. So if I could solve the full nonlinear thing from scratch at like 100 hertz, I would just do it. The problem is that it's not fast enough, right? And it takes a lot of engineering work and tricks to make it go fast enough, right? And so we're just playing those tricks. And like some of the tricks involve, yeah, making approximations inside those blocks. The reason to make those approximations, by the way, is a little subtle. It's because when we make those approximations and kind of fix some of those, those linearizations, like inside the Newton solver, that means that a bunch of the Jacobians are constant. And that means that that giant Jacobian associated with like this monster problem with all these things stacked up means that a bunch of that matrix is static and doesn't change across Newton steps. So if I'm sort of clever about that, I can permute the entries in my matrix. I can permute rows and columns. And I can move all the stuff that's static to the left and all the stuff that changes at each iteration all the way to the right. And if you know how like a lot of these kind of matrix factorizations work, like LU decomposition or whatever, you basically start at the left of the matrix and you'll column-wise across and kind of do various operations to sort of triangularize this thing. So I can basically start that LU decomposition offline. And so let's say only the last 10% of the matrix is changing online. I can factorize 90% of the matrix and cache that. And then online, all I have to do is plug in the last 10%, finish the factorization, and do a backsolve. And that factorization is the most expensive part of the whole algorithm. So if I can pre-compute a bunch of that, it gives me massive speedups. Like the reason we did these tricks is for that reason. And we got a 15x speedup by doing like these pre-factorization tricks.
Thanks, that's really cool.
All right, I think we are perfect on timing. So let's end here. Let me say, before we formally end, we have a reception on the third floor. So if you're interested in talking with Zac for more, please join us on the third floor. Otherwise, let's thank our speaker again.
Thanks.